Hello Year 13, it's Mr. Cotledge here, and I'll be taking you through the mock exam that you just sat in January 2017, and we'll be having a look at my part and the practical, and if we get lucky we might even get Miss Buck to come on for a little cameo to explain her part of the course. So we'll roll through and you can skip on any questions you got right. There's no point really going through those. Just skip on the ones that you missed out, and if you can write in your improvements, use a different kind of pen, and hopefully you'll find this useful. So obviously keen for any feedback, so let me know how you got on, and if there's anything you don't understand at the end, then I'm more than happy to go through those in a bit more detail. Just come and find me and we'll spend a bit more time on it. Okay, so let's begin. So question 1 was having a look at Equilibria at Kp. So we're looking at gases here and looking at partial pressures and seeing how they work together to give us, to be able to work out the pressure of the different reactants and products. So we've got here, I'll just read it out. It says hydrogen and carbon monoxide were mixed at a 2:1 mole ratio. So that's what we started with. Twice as much hydrogen as the carbon monoxide. The mixture is allowed to reach equilibrium according to the following equation at a fixed temperature, and we have a total pressure there as well. So the equilibrium mixture contained 0.43 moles of carbon monoxide, 0.085 moles of methanol. And the first mark, start for 1 mark, nice and simple. Calculate the number of moles of hydrogen present in the equilibrium mixture. So these values here are already at equilibrium. They're not starting values. They're the equilibrium values. So we can use those to answer our question. Carbon monoxide here is 0.43. And if we look at our equation, we'll have twice as much hydrogen as carbon monoxide. So very simple, 0.43 times by 2, which equals 0.86 moles. 1 mark in the bag. Hence, calculate the mole fraction of hydrogen at the in the equilibrium mixture. So mole fraction, we're now looking at what's the total number of moles that we have, and out of all of those moles, how many are hydrogen. So mole fraction, just to write down that equation, moles of hydrogen, moles per H2 there, divided by total moles. Okay, so we've just worked out our moles of H2 at equilibrium, so we put that as 0.86, and we divide that by the total. Well, we've got our 3 values, so 0.86 plus 0.43 plus 0.085. Actually, that was a mistake that a number of people made, so see how easy it is. Just be careful with your decimal points and the number of zeros. So let's just calculate that through. 0.86 plus 0.43 plus 0.085, and we want to do 0.86 divided by that answer, and so our answer is 0.625. 3 simple figures will be fine. That's what they've given us in our question. In fact, I might make that 3 6 just to be sure, but 0.86 will get you the mark. Okay, so mole fraction 0.625. So if I'm calculating the partial pressure, if I've got to calculate the partial pressure now, so I've got to think what's the total pressure and how what proportion of that total pressure is contributed by the hydrogen. So partial pressure equals the number of moles the mole fraction equals the mole fraction which I've just worked out, 0.625, times by the total pressure. So my mole fraction is 0.625 times by my total pressure. Well, they've given that to me earlier. If I look way back in the question, they've already given me that. So I just plug that in, 1.75 times 10 to the 4. And so my partial pressure, just type that in, 0.625 times by 1.75 times 10 to the 4, which equals 10,937.5. Right, well, I don't want all of that. Let's just make that a little bit more simple. I could call it 1.09 times 10 to the 4. I'll make it 3 significant figures again and put it into standard form. I do need to include on there my unit, so I want to make that kPa. Alright, so moving down to question B. So in a different mixture of the three gases at equilibrium, the partial pressures were as shows. Write an expression for the equilibrium constant at Kp, or I've not left you much room here, but naughty of me, right? Okay, so I will have to squeeze that one in, but that's okay, I can do that. So we're going to have our Kp. So remember, this is Kp, not Kc, so Kp. Now, lots of people put the square brackets, but I can't use those. I need to, if I need to use brackets, I'll be using round brackets. So it's products over reactants. So I'm going to put P and then CH3OH over, and I want to use those round brackets, and I want to put P of H2 squared. So I put the square in there because I've got my 2 in front of the H2 here, and then I want to put CO. Just remember, because this was a common mistake lots of people doing this, square brackets, you can use those with Kc, because square brackets mean the concentration of. In this question, we're looking at pressures. You don't want any square brackets, we just want round brackets in the normal fashion, just as you would do in normal maths equations. So there's my equation. So I'll move on to part 2. And it says, calculate the value of the equilibrium constant Kp for this reaction under these conditions and state its units. Well, relatively straightforward. I can just insert now those different values. So just got to be careful to get the right one in the right place. I've got methanol as 2710. So 2710 divided by my hydrogen, which was 12300. And that's squared. And the pressure of the carbon monoxide, 7550. And if I put those together, and I'm just going to type that in my calculator here. So I've got 2710 divided by 123, and that's squared, times by 7550, which equals another big number. I'm going to just take 3 significant figures. So I'm going to make that 2.37 times 10 to the negative 9. So that's going to give me a couple of marks. My third mark is for getting these units. So for units, I just need to work that one out. So I'm going to add those in like this. So remember, these are pressures. So wherever I've got the number, sorry, I probably can't see that. Let me move that. Wherever I've got the number, I'm going to add in my kPa. I'm proportion, I'm using the K in here. Yeah, so I've got K in the question. I need to use that here in my answer. And I've got another KPA. So I can cancel those two because they're the same, which means 1 over KPA, and that's squared. And if I just invert that, it's going to become KPA to the minus 2. Just, of course, the K here doesn't become minus 1. K is just 1,000 of pascals. So the K doesn't change. But the pascals I need to put to the negative 2 to invert the fraction. Okay, excellent. Let's move on to the next. Okay, so we're now looking at question 2. And we've got here looking at some trends of period 3. Okay, and it says, state the general trend in the first ionization energy across the period. So remember, our general trend is that the ionization energy is going to increase. Remember, the extra electron is going to go into the same shell, but we've now got a greater nuclear charge, greater positive charge in the nucleus. So it's going to go up, down. This is the one that goes up, down, like that. So the general trend is going to increase. State how and explain why the first ionization energy of aluminium does not follow this general pattern. So state how. This is where lots of people missed out. They jumped in straight on the why. They knew the answer, boom, boom, boom. But they've dropped this quite simple mark for stating how. So if I've got aluminium, well, how's it going to be different? Well, it's going to be lower. But lower than what? Lots of people said it's lower. Lower than what? Lower than, I don't know, let's see, lower than silicon, phosphorus, sulfur. What? Lower than what? So we've got to be a bit more specific. So we could say the how part, and I could actually physically write down on this how, I could say lower than expected by trend, as in it's lower than that trend line, so dip. Or I could even go be a bit more serious and say lower than magnesium. Either of those would be fine, they get me the mark, but I'm giving it a context. I'm not just saying lower, I'm saying, well, how's it lower? What's lower than what? The Y part is then to think about, well, why is that lower? So additional electron placed into 3p subshell. And what is it about that 3p subshell? Well, the 3p subshell is at excuse me, at a higher energy level, and so is easier to remove than a previous 3s electron, as it's easier to move than the one for magnesium. So just to explain that, remember you've got your energy levels, and remember your different boxes. So there's my 3s, and I'm sure this is probably coming back to you now, and I've got my 3p in here, and I've got 3 for 3p, three different orbitals within that 3p subshell. And in aluminium, I'm beginning to fill up that higher energy level, that higher 3p, and so it becomes easier to lose. Okay, right, let's move on to question 3a. Right, question 3a was a corker. Love this. It was caught a lot of students out, actually, a lot of you out on particularly the shapes and also the conditions, partly because it is a bit unusual. We haven't come across this in lessons. It's not something that we've taught, but what we have taught is just about a normal alkene and how that alkene can convert to an alkane. Imagine the hydrogens are on there. And effectively, we're doing the same process here because that benzene delocalized ring contains extra electrons, and we can break down that ring and add in some new hydrogens. So it's an addition reaction. So it says 3 parts. Glad to see that everyone made an attempt on all of these. I didn't miss any out. So the reducing agent for this conversion, well, there's a variety of things we could do. H2 is the perfect answer. We're literally just physically adding that, which is quite straightforward. But what we could say as well, and we'd also get the mark, is something like our nickel, which was the catalyst, remember? So that was the catalyst. Just to show off our knowledge, we could put that in there as well, should we have wanted to. Empirical formula of the product. Okay, so these two are linked. And if I'll just take a space down here at the bottom to draw this out. So here's benzene. There it is, we've got that extra ring. So on each of these carbons, there's space for only one more bond. Okay, so let's have a look at cyclohexane instead. So there's our cyclohexane. Now, because we've removed that ring, the carbon still needs 4 bonds. So each of these carbons has a space for 2 more hydrogen atoms. So now, surrounding that carbon, we've got 4 bonding groups, whereas surrounding the carbons here, we've only got 3. That's our big difference. If I just keep adding those on, just for clarity, all of these carbons exactly the same, symmetrical molecule, and if I was to add it up, I'd end up with the formula C6H12. Just to remember then, empirical formula, let's go back to that. This was about an empirical formula. Empirical meaning the simplest whole number ratio. So my empirical formula is not C6H12. I've got to make it simpler. I could make it CH2. My bond angles, okay, so here I have 3 bonding groups. So that's going to be a trigonal planar shape. And my angle in here, which is what it's after that angle. And effectively, it's going to be 120 degrees. In the that is the benzene. And for the cyclohexane, I'll just swap that around. Cyclohexane. The bonding angle, so again we're looking for the bond there. I've got 4 bonding groups around that carbon. Okay, so if I was to draw that carbon out, I could draw it like this. A little wedge there. I'm just going to call that R. It's our regular tetrahedral. So that's going to be a 109.5 degrees. So when you're doing these angles, you just got to make sure that you've added on the atoms that are attached. And I would physically write it down like this, just to make it really clear in your own mind what it is that you've got. The fact that you've only got 3 here and you're now changing it to having 4, and the difference that that makes with the angle. All right, so we're moving on. We're getting on to some of the GC organic stuff. And I was really pleased. Marking this one, lots of people got this spot on. But where people were falling down was not that they're not just bad, they're just making silly little mistakes. So we're going to try and highlight a few of those as we go through. And hopefully that will clarify those issues and we won't be dropping those marks again. So we're looking at a bit of TNT here. So it says many aromatic nitrogen compounds used as explosives. One of the most famous, 2-methyl-1,3,5-trinitrobenzene, also called trinitrotoluene, or TNT. This compound was shown below can be prepared from methylbenzene by a sequence of nitration reactions. So we'd start with just the methyls. We start just with the CH3 and gradually add on those nitros to form TNT. And this question is going to be about that nitration. So it says here, the mechanism of the nitration of methylbenzene is electrophilic substitution. And the first question is about the reagents. So just to highlight about this mechanism, if you remember that the benzene is quite a stable molecule, and the reason for that stability is that we've got delocalized electrons. So despite its appearance, the fact that you've got that area of high electron density, the fact that those electrons, those extra electrons, kind of spread around the ring increases the stability. So it is going to be electrophilic, so something's going to be attracted towards those electrons and disrupt that ring. However, it needs to be quite a powerful electrophile. So for this case, with the nitration, the electrophile we're going to be looking at is the nitro ion here, NO2+, and that will swap, or has swapped in this case, with hydrogens around the benzene. So let's get into the questions. It says AI here. It says give the reagents used to produce the electrophile for this reaction. Write an equation to show the formation of it. So the reagents used to form it. Now, we need to get that NO2. It's going to come from nitric acid, HNO3, and it's going to come from that as that reacts with H2SO4, and effectively the sulfuric acid is going to prize off a hydrogen. With that, it's going to have a reaction there. But now where people were dropping marks was that they weren't making the point that these have to be concentrated. You have to get conkin to get these to react and form that electrophile. So you actually get 2 marks. So that the equation then is our HNO3 plus the H2SO4, and we're going to form those different ions. So we're going to get HSO4 minus, so we've lost our proton here. We've got an NO2 plus. Doesn't really matter where that positive goes. Strictly speaking, it's on the N, because it's going to be the N that then goes on to bond with the benzene, but it doesn't particularly matter. And then we also have, I should put plus there, shouldn't I? And then we also have H2O being given off. So that's our equation. There's our electrophile. Let's get into a bit of the mechanism. So part 2, outline the mechanism reaction of this electrophile with methylbenzene to produce. Now this is crucial. People were missing this off. We've got 4-methyl-nitrobenzene. So methylbenzene is obvious, but let's just draw our product. So we're going to have our CH3NO2, and we've got to that from methylbenzene. So it's very important that this nitro is going to come into position 4 on that benzene ring. Or rather, I should say that this is position 1 and that's position 4. But it should be the opposite side of the ring. Now that's really important because that's not the case in a lot of answers. A lot of people were diving in here because they knew this mechanism really well, which is pleasing to see, but got to make sure that we've got it the right way around. So I'm drawing this again. I just drew it there. I don't know why I'm doing this, but anyway, here we go. Just enjoying that hexagon with a beautiful little circle in there. Right, so we've got NO2 plus, and we're going to put that there. Now, the obvious thing, because this is so often how we draw, we put a line going across here and we attach it in here. But that would be at position 2. It actually needs to come in on this far side. So I'm going to draw my arrow going all the way around like that from this far side. And so I end up with my intermediate and my broken ring with the positive charge down here at the base, whilst the CH3 is at the top. but they're on opposite sides. Incredibly important, a few people miss this off, that positive needs to be next to the addition of the NO2. Okay, I can't have that half a ring pointing the other direction. It wouldn't make any sense. It's got to be next to where the NO2's come in. And then, of course, those electrons are going to come back into the ring. And so we're going to finish off forming the NO2. All right. Part B, it says deduce the number of peaks in the carbon. So looking at carbon first of TNT. So we're not looking at the one we've just done here. Let's ignore that completely. We're going all the way back up to the top. We're looking at carbons. So we've got 1, 2, 3. Remember, there's carbons in all of these points. Right, how many peaks do we have? Let's think. Now, this molecule here, if I sketch a line down there, is symmetrical. Carbons on that line of symmetry count. So I've got 1, 2, 3, 4, 5. This one and this one are going to they're equivalent, so they're going to produce the same peak. You don't want to see distinct peaks between those two. Likewise here. So I've got 5 distinct carbons. Answer down the bottom, 5. Right, part C is looking at hydrogens this time. I've kind of messed up my TNT here, but anyway, we'll have a go. So I've got some H's up here. Well, obviously they're unique, as it were, because they're up there by themselves. No other CH3 groups, no other methyls. Remember, and I could add this in if I want to just clarify it for myself, 2 hydrogens here, but I've got no hydrogens where any of these other bonds are. Yeah, because the carbon on the benzene can only make 3 bonds. These 2 hydrogens are going to be tied, they're going to be equivalent, which leaves just the hydrogens in the methyl making 1 peak and these making a 2nd peak. So back to my answer, 2. And then D, use the molecular formula, write an equation for the decombustion reaction that occurs on the detonation of TNT. Sounds exciting. Right, okay, so decomposition. So it's breaking down. It's not reacting with anything as such, it's just breaking down. Remember the classic from year 10, bit of thermal decomposition. Decomposition is like breaking down into smaller parts. So we're going to go through the same process. So C7H5N3O6. And it says, what's going to break into? I don't know. In this reaction, equal numbers of moles of carbon and carbon monoxide are formed together. So carbon, carbon monoxide, together with water and nitrogen, H2O and N2. Right, so I'm going to get equal numbers of moles, equal in here. So equal amounts of the C and the CO. Oh, but I've got an odd number here, that's a bit awkward. Well, I could do 3.5 of these each. Don't particularly like that, so what I'm going to do is I'm going to double this. So I've got 14 carbons, which means I need 7 of each of these. I've now got 10 hydrogens in total, the 5 times 2. So I'm going to need 5 of those. And the nitrogen, I've got 3 times 2, 6. So I'm going to need 3 of those. Awesome, right. Let's get on to the juicy bits. Okay, welcome back, ladies and gents. I've had a little bit of a breather, so back on form now. And what a question to get back to. This was a screamer, loved it. And I was pleased when I found this one. It was a bit of a tricky number. So let's get through it. And well done to those of you who got it right. And those of you who weren't sure, I suspect you might be kicking yourself in just a little bit. So it says, this question is about some isomers of C5HAO2. Compound H is a cyclic ester and can be prepared as shown. So here's H down here. Now, it's a cyclic ester. in nearly every way, it's exactly the same as a normal ester. The cyclic nature of it just means that we're going to have slightly less hydrogen atoms on there. But we can see, if I kind of highlight this area here, that this is our ester part, this is our ester grouping. Again, it's exactly the same as if it was a straight chain ester. And so what was it formed from? Well, we've got a straight chain, and on one end we've got our COCl, so remember that if I write that out, that looks like this. And on the other end we've got a normal alcohol group. And effectively what's happening is that those two groups, those two end groups, are reacting with each other. So the molecule is, as it's rotating around, as those bonds are able to, they're all single bonds, as those bonds rotate around, there will become a time where either end of that molecule comes into proximity of the other. And at that point, those two ends are able to react. So we've got our two functional groups here that can react together to form an ester. And it doesn't matter in any sense that they're on the same molecule. So let's get down into the question. It says name and outline the mechanism for this reaction. So wherever we see the C double bond O, and that C double bond O remains over this side, we should be thinking about addition, elimination. So we've got the double bond there that's able to open up and allow new atoms to come in and to be added to the molecule. But the double bond remains in the product. So at some point, some atoms have to be removed. So we've got an addition, elimination. So opportunity for atoms to be added, but those atoms have also been removed because we've got the double bond reforming. So it's an addition, elimination reaction. So that's the name. Can tick that bit off. I've got to do the mechanism. There's three parts of this. Let's take them each in a go. So mechanism. This is going to be a bit awkward to draw, isn't it? I bet you all found it quite tricky to draw this one out. How am I going to do this? Right, let's start with the bits that are important. So I want to get my C double bond O and my Cl. And I need my OH coming in there. And how many other carbons I've got? 1, 2, 3, 4. So 1, 2, 3, 4. Oops, left that one a bit small, but anyway, it doesn't matter. And I need to add my H's in. So that straight chain is going to curl around, wrap around, so that the functional groups can get close to one another. And at this point, we can begin to see what's going to happen. So the chlorine, electronegative. The chlorine is electronegative. So that's going to be drawing electrons from that bond towards itself. It's going to, our oxygen is also electronegative, so our carbon in here is going to be electropositive. If you look at the other end, we've got an electronegative oxygen and a slightly positive hydrogen. So, and we've got our lone pairs. I could draw those in as well. Right now, so one of those lone pairs from the slightly negative oxygen is going to be attracted in towards this slightly positive carbon, and that is going to form a bond. The carbon itself can't hold 1, 2, 3, 4, 5 bonds. So one of these double bonds is going to be kicked out towards the oxygen. First stage. C, got to try and draw this out again. I can now use my template of my previous molecule to try and draw it. I might just pull that up a little bit so that I can get that in there. I've got a single bond now to the oxygen. I've got the Cl out here. That oxygen is now collected up 2 electrons. It was sharing them, but now it's taking those electrons back to itself. So in essence, it's gained 1 electron. So that now becomes a minus. Don't know why I circled it, didn't need to be. I was getting into marking mode there. I've got my oxygen down here. That's still attached to a hydrogen. So that was with 2 lone pairs. One of those lone pairs is now sharing. So it had 2 negative electrons to itself. It's now sharing them. So it split those between itself and the carbon, which leaves the oxygen slightly positive. Really important, because now we've got, if we look at that whole substance together, a neutral substance. And if we look at this whole substance on the right, it still remains as an overall charge as being neutral. Remember, the overall charges have to always match. So what's going to happen next? We've done our addition part, so now's for the elimination. So we're going to have a lone pair come back in, reform the double bond. That's going to kick out, so we're going to lose our chlorine. And I'm going to add it on this one as well. The electrons of this bond are going to go back in towards that positive charge, removing the hydrogen. So let's draw it one more time. And just got to make sure I get all these. It takes a lot of concentration, this, doesn't it? Getting it all in the right place. Right, there we go. Double bond O. Cl's come away. H has come away. I didn't add my H's on the last one, but I will do here. Make it look pretty. Make it look complete. Just to make sure, let's just check that what I've created here is the same as what's in the question. Yep, looks good. Looks the same. Fantastic. The 2 parts that have come away. So we've lost a Cl that's taken the electrons, that's a minus. We've got an H plus that's lost its electron, so that's going to become a hydrogen. Those 2 are going to combine, and so we're going to get an HCl being formed as well. Oh, a bit of a marathon that, isn't it? But it's good. It looks nice. You're going to have to watch me now add all my hydrogens in. Can't leave it looking like that. Right. So, mechanism, check. Next bit. Use table C on the data sheet. Oh, let me... I've got my data sheet to give the carbon NMR value for the carbon atom at A and the one at B. Where's A and B? Okay, so we're looking at the one here and the one here. So just a case of going through and checking those values. I'll just make it really clear. So A equals, so I'm looking at the one here. So I'm looking at a carbon with a hydrogen, but it's next to a carbon with a double bond O, which is next to the oxygen. Let's just check through on this, just check. So I've got the carbon, looks good here. Just check the other options. Is that the best one? Only other one next to a carbon are these ones, but that's looking at the carbon on the double bond. So this one here is from the carbon that's next to the double bond. So I'm going to go for that 20 to 50. And B. So this time I'm looking at the carbon with the hydrogens, and the interesting thing is it's a single bond to an oxygen. So let's have a look for that one. Just scan them through. Okay, we've got a carbon next to an oxygen. It says alcohols, ethers and esters. We've got an ester here. So that's going to be 50 to 90. All right. We could put in the parts per million, but we don't really need to. ppm. There we go. Done. And I can tick that part off. Is that everything I need to do? Just double check. Looks good. Okay, cool. Right. Okay, so moving on to part B. We're still looking at some organic chemicals, and from the looks of it, J is going to be a ketone, and K, we've got a ketone there and an aldehyde on this end. It says, state how you could distinguish between those two compounds by a simple test tube reaction. Right, test tube reaction. What could I do in this? And so, first off, let's get that in. Right, we've got a aldehyde, we've got a ketone. So we could use an oxidizing, the fact that aldehyde can be oxidized into a carboxylic acid, but that the ketones can't go any further. They can't be oxidized any further. And I can use that in my test. So I could use Tollens. I can never remember it's Tollens or Tollens. It's Tollens. This way around. Tollens. So Tollens, and what's that going to do? So that's my reagent, Tollens reagent. That's my test. With J, there will be no reaction due to ketones. I don't really need to put that extra bit in because it doesn't actually say that, but let's chuck it in there anyway. With K, are going to get the reaction. So reaction forms. So Tollens is the test for an aldehyde. It forms the silver mirror. Done. State how you could distinguish J and K by giving the number of peaks in a proton NMR. So this was the test tube. And now we're doing the 1H NMR. What's going to be the difference? So now I'm looking at hydrogens. Let's have a little quick scan. So this J is entirely symmetrical, isn't it? If I put my line down the middle there. So the hydrogens here and here are equivalent. So they're going to contribute towards the same peak. And then I've got a second peak here in the centre. So with J, 2 peaks on the spectrum. With K, what's going to happen with K? Let's check. So we've now got a non-symmetrical. So all of these different hydrogens are going to form their own, are going to have their own distinguishing peak. So we're going to have 4 peaks on spectrum. Okay. Moving on to question C. Now I know these ones are a tricky number, especially in the sort of the stress and the pace of an exam. Trying to make sure that you've got all of these in the correct place, your mind's racing, can be quite difficult. I think often the key to this is remembering that they've given you the formula. So whatever we produce in our answer, whatever we put down, whatever molecule we arrange, it has to be an isomer with this particular formula. So it's a really simple way of checking whether what we've done is correct. So let's go through them in turn. Again, I haven't really left you much space, just saving those trees. Let's have a look. L, right. L, oh, that's a nice straightforward one. So we're just going to write down what it is. So methyl 2-methyl propanoate. Oh, I've just got to be careful because of that E, propanoate, because that's quite rare to see that. Methyl and an O8. So we're going to have an ester. So I might just draw in my ester group there. The methyl comes first. That's come from the alcohol. So methyl goes in there. The OH part is always the bit that's attached to the C double bond O. O8 with the C double bond O. So from the carboxylic acid. And now I've got a propanoate. Right, let's just get that in. So prop, so it's going to be 3 C's. And we've got a double bond. Well, where's my double bond going to go? It can't go on this carbon, can it? Because if I put it here between the carbons here, then my carbon, this number here is going to have 1, 2, 3, 4. And if I put a double bond in there, it'd have 5 bonds. Well, we know that carbon can't have that. So that double bond for the N part must go between those carbons. I've got a 2-methyl, that's the last part just to get in there. So I'm just going to put another carbon in. And to finish with, I'm going to add in any extra hydrogens. And I nearly made the mistake there of putting in 3 on the end. So just check, carbon's got 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, yeah. Everything looks happy. Let's just check the numbers just to make sure. So I've got 1, 2, 3, 4, 5 carbons, yes. 1, 2, 3, 4, 5, 6, 7, 8, yes. 1, 2, yes. Happy with L. Let's move on to M. And I'm just going to cover that so I don't get confused. Right, M. So M is an ester that shows EZ stereoisomerism. And I've got this as my formula. I know from the previous question that I'm going to need a double bond in somewhere in my chain. Otherwise, I'm going to have the wrong number of hydrogens. Okay, so I need to keep that double bond around. And because it's an EZ, I'm definitely going to have a double bond. It's going to be an ester. So let's try and get my ester group in there first, because that's the thing I definitely know I've got. So an ester is going to look like this. I've used up part of my atoms already. An ester that shows EZ stereoisomerism. Where shall I go? Let's put my double bond down here, I think. Double bond C. So that one can have an H. That makes those two groups different. I need, for EZ stereoisomerism, remember I need 2 different groups on each carbon. So I've got 2 different groups there. I need 2 different groups on this carbon. So I think what I'll do is I'll have one as a carbon and one just with an H. So that could then have, let's finish that off. So I've got 2 different groups on this carbon. I've got 2 different groups on this carbon, EZ. Right, let's check numbers. 1, 2, 3, 4. I've got one more carbon to add in. So I've kind of sealed off that end, so I'll put it on this end. And that means that's going to be 3 hydrogens. So let's just add in the hydrogens. 1, 3, 4, 5, 6, 7, 8. Yes, and I've got 2 oxygen. Done. Do you see how I'm adding what I know for sure, getting those sure bits in first, because that leaves me less to tinker with afterwards. Let's go N. Is a carboxylic acid with a branched carbon chain and does not show stereoisomerism. Right, so the thing I know for certain is it's a carboxylic acid. Let's get that in. It's got a carbon, it's got a branched carbon chain. So I might just put my branch in there. That does not show stereoisomerism. Okay, so remember I've got EZ, and the other type, I've just got to be a little bit careful. I've just to watch out I don't accidentally make an optical isomer. I've got those 2 types. So 1, 2, 3, I could have another 2 carbons, and I've only got 8 hydrogens, so I've got to remember that I need to include a double bond somewhere, but also that my double bond can't show stereoisomerism. A little bit awkward. What I might do is go 1, 2, 3. I know I've put that line in there, but I might actually make that my double bond, put 2 H's on that end. All right, now I've sealed that off. I'm definitely not going to have a EZ. I'm going to have 2 H's up here. That carbon that's in danger of being an optical can no longer be an optical. And I need my branch. Let's put a carbon in here. Oh, a bit tight. Bit of a messy molecule, not so happy with that one, but let's just check I've got the right numbers. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. Yes. 2 oxygens. Yes. Just double check. No, there's no EZ isomerism. And there's no optical. I am good to go. Right, P. Bit messy that one, not so happy with that, but anyway, never mind. P. Right, now we're going for optically active. What I can picture what I did last time. So C, double bond O, OH, carbon in here. Optically active. Right, I reckon this carbon should have 4 different groups attached. So one of those can be a hydrogen, that's nice and simple. Let's put 2 carbons. 1, 2, 3, 4. I've got another carbon, 5. Put on my hydrogens. Yes, yes, yes. 1, 2, 3. That needs one more hydrogen. That's got 2, so this needs 2 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 2. Done. See, when you're actually in the rhythm, it doesn't take long to check those numbers, does it? You can really quickly whiz around. And the final one, Q, is a cyclic compound. Interesting, a bit different. Cyclic compound that contains a ketone group and has 2 peaks. Only 2 peaks. Okay, right, cyclic. I've got a ketone. Only got 2 peaks. And it's the proton. Okay, so what? It's going to be a cyclic. Okay. So it's got to be symmetrical. Contains AQ. It doesn't give me a clue about that other oxygen. So what's that other oxygen going to do? Let's just play around with a few things. So let's put another ketone in. 1, 2, 3, 4, 5. And I'm going to add my hydrogens. Doesn't work. I've only got 1, 2, 3, 4, 5, 6. Alright, so that one, let's scrap that. That was a rubbish idea. Okay, let's try again. So you see, this is a bit of an awkward one. So I've just got to give it a little bit more thought. Where else could that oxygen go? It could be an OH, but if it's an OH, just looking at this, if it's an OH, that means that these three are going to be different because it's no longer symmetrical. I was looking for that line of symmetry. So I've got to come up with something else. Let's try this. So C double bond O, C, 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 O. 1, 2, 3, 4, 5, 6, 7, 8. We've got our line of symmetry. Oh, obviously I wouldn't draw that in if this was my paper. It makes it very confusing. I've got a line of symmetry and I've got 8 hydrogens. So my numbers all match and I've got my various pairs. Bingo, that's the right one. Okay, we've got it. Q. See how this side and this side are equivalent. So that's one pair and a second pair. So I get 2 peaks only. Done. Okay, so we finally made it to the multiple choice on my side of the paper. And the first question here is asking me about a race mate. So obviously I've got to remember what a race mate is. So that is 2 equal amounts of enantiomers. So I've got equal mixture of enantiomers. Remember, enantiomer is from optical isomerism. So that's the 2 different forms of isomerism, just making sure that I've got equal amounts of those. So where we've come across this is when we're looking at these planar, in fact that's not very clear, let's just do that again. Where we're looking at planar molecules, we've talked about substances coming in above and below the plane, forming optical isomers, but there's an equal opportunity for it to come from above and below. So that's the context. Let's have a look at the options. So I've got an HL on the end, so I've got an aldehyde. There is, here we have a ketone that's towards one end. We've got a ketone that's bang in the middle, equal either side. And we've got an aldehyde again on the end, or an alkene. So remember, for an optical isomer, I need 4 groups attached, 4 different groups. 4 different groups attached to a carbon. So if I'm looking at this, well, I know it definitely can't be C, because where the action is going to happen, that carbon is attached to even or symmetrical alkyl chains. So if I just very quickly draw that out, I've got a C2H5 and a C2H5. So I've got symmetrical chains here that can't ever show optical isomerism. On the end of the chain, don't like the look of that one because we're likely to get a couple of H's next to each other just because we're on the end. So we're looking for something in the center of a chain but which has different alkyl groups attached. So the best bet looking at this one is looking at B in here. So B, we're going to end up with, not double bond, an OH, an H, a C3H8, and a CH3, 4 different groups around that carbon. Bingo. They're quite a bit of work, aren't they? It takes a lot of sort of thought to get to these answers on these multiple choice. So you do need to leave yourself a bit of time just to give yourself that opportunity. Let's have a look at question 7. So 7, in which the following is clearly, oh, this might be a bit more straightforward. So we've got this one here, just looking at it closely. It's coming in towards the carbon. Well, that carbon's going to be slightly positive, slightly negative. We've got a substitution going on. That's fine. Used incorrectly, so I'm looking for the one that's wrong. It's coming away from the double bond, looks good. And then that's coming and splitting up with that one there. That's fine. From the negative pair of electrons towards the positive carbon, that's fine. What I'm looking for, often what they like is an arrow that's going in the wrong direction, or perhaps not coming from a bond but coming from an atom, so it's not originating in the electrons. So remember, the arrows always show the direction of the electrons. So let's get down to C. You've got the lone pair of electrons going into the carbon, double bond breaking, looks okay. Right, here we go. So, unsurprisingly, we've got an arrow that's going the wrong way. So the arrow is going towards the hydrogen, when look, we've got a positive charge there. Surely those electrons would rather go, those negative electrons would rather go towards the positive charge. So that is wrong. C. Just to make sure, let's check D. Coming from the bond to the positive, yeah. From the bond in towards the bond here, yeah, all good. So that one's fine. Lastly, CH2O is the empirical formula of. All right, let's just write these out. Methanol, CH3OH. No. Oh crikey, methyl methanoate. Right, here we go. So we've got C, O, C, double bond O, H, 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 2 carbons, 2 oxygens, so we've got a C2H4O2. Ooh, I like the look of this. That's going to become CH2O. So that looks good to me. I would, if I was pressed for time, right, I've got it, move on. But just for the process of this, let's just show you those other ones, because I'm pretty sure we're going to find that these are wrong. And yeah, we've got far too many hydrogens there. We've got 6, so that's not going to work. And the butanal, well, I can say before I've written it out, we're not going to have enough oxygen, are we? Yeah, so wrong, B's money. So I'm back. I've come right the way back to the final section of the paper, looking at the practical. I've left out Miss Buck's questions, and as I say, hopefully she'll get onto a little cameo at some point. We'll line that up as soon as we can. So I'm onto the back. I'm looking now at those practical questions. So I'm looking at particular experiments, particular observations, particular methods, and will gradually build up a bit of an idea of what sorts of questions they're coming up with. So far in our experience, it seems as if the questions are quite predictable, and I'll talk a bit about that as we go through. So we're looking at question 20, and the first one is about observations. So we've got a reaction taking place. What are the observations that we would expect to see during that? So write an equation for the reaction that occurs between magnesium, or when magnesium is heated in steam, of course being gaseous water. So Mg plus H2O, just for completeness, let's put those state symbols in. So we've got solid magnesium, we've got water as a gas, and the magnesium is going to take away the oxygen, break up that water, and we're left with hydrogen. So you've got a gas, and this is a solid. Observations, well, what do we see? MgO, what do we know about that? That is a white solid with these period 3, if in doubt, go for white. 9 times out of 10, we're looking at something that is white. So I've got a white solid, and also I've got my magnesium. When we burn magnesium, it's going to be a white flame. Question B is very similar. So we're looking at sodium now, and as it's heated in oxygen. So sodium Na is going to be a solid plus O2 gas, and we're changing that. We've just got to make sure we get the numbers right. Remember, Na forms that +1 and oxygen is -2, so we're going to need 2 of the Nas to make it balance out, and then I've got to just balance the whole equation. So I need 2 of those. In fact, I need 2 of these, don't I? Which is going to mean I don't need 2 of those, I need 4 of those. And I get my answer, Na2O. Let's put that in S, just for completeness. But we don't, the state symbol we don't get a mark for, so we don't need to worry about that really. 21A, let's have a look. So during the preparation of aspirin, it is necessary to filter the crude oil under reduced pressure. Ah, the good old Buckner. Right, reduced pressure. So I know this was a long time ago. This was last summer when we're a bit all over the place, aren't we? But we did those practicals. One of the bits of apparatus we were using in that was a Buckner filter. So, sorry, it says draw a diagram to show the apparatus. Blah, blah, blah. Do not include the vacuum pump. So was the Buckner filter. So we had that porcelain flask. It was quite a sort of flat bottom, wasn't it? Except for that's a bit of rubbish. That's not even, is it? Anyway, never mind. And we had filter paper lying over that. And that goes into a flask. And our flask, to get that reduced pressure, our flask had a sidearm on it, and that would be to vacuum pump. So we've got our flat bottomed filter here, that's supposed to be flat, that's our Buckner, and we've got the flat conical flask with the sidearm. Just put it both in, we've got the filter paper in there, and that the vacuum pump here is going to suck some of the, it's going to pull some of the air out from the flask, reduce the pressure, that's going to pull the liquid down faster from here. So we get a mark for getting the sidearm. Sorry, I've just noticed my bung here is really weird. Anyway, let's just do that bung again. There you go. We get a mark for getting our sidearm flask, and we get a mark for having our flat Buckner filter. In fact, I'll just go and grab, bear with me, I'm just going to go and grab one to show. So as if by magic, I've just miraculously appeared with these. I've got my sidearm conical flask, so that's where I want to attach my pump to. Move the green pen, and I've got my filter. Okay, so that would be what it looks like. Now I need to draw that, so I need my flat bottom. If you look inside the filter, remember it's got those small holes, it's got a flat base, and I need my side arm here to get my marks. Question B, it says, you are provided with a small sample of pure aspirin in a melting point tube. Describe briefly how you determine the accurate value for the melting point of aspirin. So when we've done this, we did this again in the summer. Remember we used those tiny thin tubes, the capillary tubes. Remember we were dabbing it down and we were collecting up little tiny pieces of the aspirin to analyse. So once we'd done that, we then inserted that very thin capillary tube into the melting point apparatus. So place capillary tube with sample into, and this is where we get a mark, melting point apparatus. Literally that's what it's called. It's like Ronseal, does exactly what it says on the tin. And what do? We then, well, it was automatic really, wasn't it? You press the button, the machine ramps up the temperature. We're looking down the eyepiece to see when that sample melts. But the important thing is that on our prediction, where we are hoping for it to melt, we then slow that temperature increase very, very slowly, so that rather than just seeing that it's somewhere within a region of 2 or 3 degrees, we can get a very, very precise, accurate reading for when that sample melts. So slowly, very important, slowly increase temperature near melting point. It's not really even a sentence, is it? But anyway, it makes sense. It gets us our mark. We can move on. Okay, we've got a great long list here of all sorts of instructions, and I could read that all out, but I'm not going to bother because the question's actually not referring to anything in there. So it says here, state the purpose of the anti-bumping granules. Well, anti-bumping granules, they always do the same thing. So the reason we're putting it in there is to stop any large bubbles appearing as we boil a liquid. So we're keeping a smooth boiling. Again, these are just little catchphrases, important phrases to remember to pick up the marks. So reduce vigorous. They don't like vigorous for some reason. Vigorous boiling. So for some reason, that's the phrase we want to use. We want to have smooth boiling. We don't want vigorous. Use that. We get our mark. Hopefully you remember, just in case if we've got our beaker, we've got some water in there. Remember we added those little glass beads, and they kind of sit around the bottom. Those glass beads, they're the anti-bumping granules, just in case you'd forgotten. Right, B, name the part of the distillation apparatus where cyclohexene vapour is changed back into a liquid on the distillation apparatus. So to go from the vapour back to a liquid, we're having to cool it down. We want to cool it down quickly so that it turns into a liquid before that vapour can escape. And so what we do is we use a condenser. And the condenser cools the liquid down very fast. And a diagram of that. Right, so remember the condenser is effectively a tube down which the liquid is, down which the gas is going to flow. And as it flows, it's going to be cooled. And it's cooled because that tube has got a jacket on it. And I want to draw my jacket like this. So imagine I've sliced that tube in half. And I have here water in. I don't actually need to add these labels, but anyway. Oh, sorry, wrong way around. Water out. So that it's flowing against the flow of the, let's say, gas is flowing in that direction. It's going to flow against that flow. Water in. So you have a negative gradient. what do we get our marks for here? Well, we get a mark for the name, and we get a mark for showing that our condenser has this jacket. They call it a jacket filled with water that's going to cool it down. Done. 2 marks. So again, final question. Oh, hey, we're getting there. We're nearly finished. An equation for the decomposition of hydrogen peroxide is, and it's shown there, the rate of reaction is determined by collecting the oxygen. Of course, oxygen is a gas formed, and measuring its volume at regular intervals. Draw a diagram to show how it can be collected and measured, not just collected. Noticing a pattern here, we're getting lots of drawing apparatus, but the drawings can be relatively basic. There's a few things to pick out on each. So let's get our reaction going first. We want our reaction to occur in that's supposed to be a conical flask. It's not the best, is it? But you can tell what it is. And out of that conical flask, we've got a tube, and the flask is bunged. And that tube is going to connect up to a vessel where we can collect the gas and we can measure it. So what we're looking for is a gas syringe. Now that will do for a syringe, doesn't need to be any more complicated than that, except for to measure it, we need to put these lines on. As you can see, it doesn't need to be very accurate. I'm just kind of randomly sketching them in there. But you need those lines in to show that as the gas is collected, we can see the volume that is collected. Experiment could use results to determine the initial rate. The initial rate, so how do we get the rate right at the start? Remember, rate is the change in the amount of product or the amount of reactant over time. So we could, if we've got the volume of gas, we've got time along here, the volume of gas we produce is going to be really high at the start. It's going to go really high, and then it's going to peter off and then become flat as that reaction finishes. We want to know the initial rate. Well, to work out the rate at any point along here, we find a gradient. So at the end where it's flat, the gradient is 0, nothing's happening. It's going to be relatively shallow here. The start is where it's going to be its steepest. So we take a tangent, and we work out the gradient. So tangent at t equals 0 at the start. So tangent to gradient, tangent to line at t equals 0, then calculate the gradient. And I should probably add tangent to line. I've drawn this, but imagine that's not there. I can't just write tangent to line. I've got to say what line am I talking about, so I should have put in there graph of volume against time. Excellent. Right, well, I hope that was helpful. We're very happy to hear any feedback, what would be more useful. If, of course, you want to go through another question in a bit more detail, just come and find me or Miss Buck, and we're happy to talk about that a bit more at length. And we can do that on a one-to-one and be really specific. But hopefully this has gone through and shown you a few of the easy errors that you've made, and where you can pick up some easy more marks. If, as I said, if there's something more particular, come and find us and we can go through that. All right, good stuff, guys.